Hello physics students, this is Mr. Steinerson, and in this recording I want to give you an overview of Hooke's law and also how we can determine the amount of energy stored in a spring when that spring is stretched. And so when we take a look at this example, and especially with springs, we're going to use some main assumptions that we're going to come back to, and one of those is that there's a uniform amount of stretch added to the spring. All right, so that force is going to be a uniform force, and also that the spring itself is never overstretched, so it can always return back to its normal shape. And these are things that are important because we want to make sure that we're talking about a Hooke's law relationship with our spring. All right, so what we see when that happens, when we have a spring that might be stretched a certain distance, that there's an amount of force that takes to stretch that spring. And the amount of force can change, and it depends on the distance that you stretch it. So if you only stretch it a little way, there's a little bit of force, and if you stretch it farther, you need more force in order for that spring to stretch. And it also depends on the type of spring material. So some spring materials are a lot more difficult to stretch for a given distance, and others are a lot easier. Now we see springs all over the place, right? So anywhere from like a spring door or even a garage door or even wind-up toys, they're all going to be able to be explained with some of these cases as long as we follow those assumptions that it's a uniform stretch and it's not overstretched. So what we're going to take a look at in this is trying to find a relationship between the force that's applied and the distance that is stretched. All right, and I went through and I actually made some graphs of this, and so I went to a simulation in PhET and I plotted how much force it takes to stretch a spring, and then I got some values. All right, so notice in the simulation, as I pull the spring back, and so I'm going to increase the displacement, the amount of force also increases. And I can, as I'm doing that, it looks like it's increasing in a certain way. So to determine what that relationship is it linear relationship? Is it an exponential relationship? How, in fact, are the force and the distance stretch related to each other? I went back and I put this into Excel to make a graph. And so here are the two graphs that I made. I made one with one spring, and then I made another one with a different spring. Each one, I'm stretching the same amount of distance, and I try to keep the numbers simple so you could probably see these relationships by just looking at the graph. So for each point 1 stretched, this is the force for spring 1, and this is the force for spring 2. Now what I did is, after I plotted these, I added a trend line, and you can see right here that this trend line definitely shows a linear relationship. So as the stretch is increased, the force increases, and it does so at the same amount every time. So it's a very linear relationship, a linear fit. And when I found the best fit, I actually found a slope of that best fit line also. So I could label this, and this is not just y, it's actually the force that's been applied is equal to 150 times x, or the displacement. Okay, and that force is measured in newtons. Same thing down here. This is not just y anymore, but it's actually force that is required to pull is equal to this other slope value times the displacement. Well, it turns out that those slope values actually represent the spring constant. And that value is related to the type of spring that you're using. So notice here, this spring constant is 260 Newton meters. That's the slope that we got for spring 2 on the Excel document. So this relationship is a very linear relationship, a linear fit, and it's going to tell us how the force and the distance are connected to each other. All right, so when I go back to my original question, what is the relationship between the force and the distance stretched? I now know I can go back to that idea of having a real linear relationship here. So force in newtons times distance, we'll just call that x. All right, and I'm going to always get this kind of linear relationship here. And the slope of that line is going to be equal to the force in newtons divided by the distance, I'll say x in meters, and that value of the slope is equal to something called the spring constant. Okay, so that actually has a symbol as well. We often use a lowercase k to represent what that spring constant is. Now, if I did go back and rewrite this, where I know that my force is my y and my distance is x, I can rewrite this as y equals mx plus b, or force is equal to the spring constant, which is the slope, times my x value. And in fact, this is the relationship called Hooke's law that is going to apply for these uniformly stretched springs. All right, so we're going to come back to this idea in when we talk about energy, but this is a big relationship that we're going to be using, and this is called Hooke's law for springs, and it defines the relationship between force and distance stretched. It always depends on what this spring constant is, and that depends on the type of material that the spring is made of, how tightly coiled the springs are, things like that. All right, our next video is going to detail how we can use this to find the energy relationships.